We discussed in lecture 1C charged particle in a magnetic field. We dealt with the cases of parallel entry or antiparallel entry, in which the charged particle moved straight, caring not whatsoever to get deflected, that is, moves along a straight line. There is no change in motion. We then discussed normal entry of charged particle in a constant magnetic field. If B is downward, say, a negative charge upon entry will follow a right-handed circle, while a positive charge upon normal entry will follow a left-handed circle. The circle that the charged particle traces has radius rho, and it depends upon mass, velocity, charge and magnetic induction. It depends upon momentum, it depends upon kinetic energy. The time period, the frequency do not depend upon velocity. Also, we recall that kinetic energy and the magnitude of velocity are constant, and this is because Lorentz force does not do any work. This was shown in lecture 1C. We did some problems in this lecture, and let us do a few more, and then we'll go into the theory. The problem involves a magnetic induction B that extends over the length A. A charge makes a normal entry into this magnetic induction, and obviously the magnetic field will bend it from its straight movement. Now B field, suppose, is downwards and the particle enters at right angles, so it will be affected by the B field, and therefore it will experience a force along this direction. It enters at P, it bends, and at Q it makes its exit. We are to find the exit momentum and the exit angle. Let us now come to the answer. The particle moves horizontally by a distance A and is pushed a distance D perpendicular to its direction of entry. A and D are both in a plane perpendicular to B, which is vertically downwards. Now refer to this figure. P is the point of entry and OP is the radius rho, and Q is the point of exit, so OQ is also the radius rho. PQ is the circular track. We draw a line parallel to the entry direction through the exit point Q. This line meets OP at right angles, so we have a right angle triangle here. We can now apply Pythagoras theorem here to get this equation. Hypotenuse is rho square. This is equal to the sum of the squares of the other two sides. Now this is rho and this is d, and therefore this is rho minus d. So we have rho minus d square here, and this is a, the length of the field, so we have a square here. Simplification gives us the value of radius to be of this amount. Again, rho is related to momentum through this equation which we have written here, and therefore the value of momentum is obtained here as P equal to rho QB, and put the value of rho to get this expression for exit momentum. Now let us focus on exit angle. If there were no Lorentz force, the particle would have traveled straight, that is along this direction, but due to Lorentz force the particle trajectory bends and it exits along this direction. So the exit angle will be the angle between the two directions, the entry direction and the exit direction. Now this is the radial direction and this is the tangent. So this angle is 90 degrees, which means since this is theta, this will be 90 minus theta. And since these two lines are parallel, this one will be 90 minus theta. Now this is a right angle triangle, so this is 90 degrees. So the sum of these two angles will be 90. Now since this is 90 minus theta, this angle will be theta. So we have shown that these two angles are same. Now looking at this right angle triangle, let us find the value of sine theta. Sine theta is perpendicular by hypotenuse. Now this is perpendicular A, and hypotenuse is this OQ, which is equal to the radius of the circle, and therefore we have A by rho. Put the value of rho to end up with this expression for sine theta. In other words, we have found the value of theta. In this problem, a particle has been referred to which experiences a damping force which is proportional to its velocity, and the particle enters the magnetic field normally. Now we have to find the nature of path, the speed and the radius of curvature of the track, the circular track which particle traces in the magnetic field as a function of time. Now let us first do the initial part, particle moving under a damping force, which you have solved in your mechanics class. Now particle experiences a damping force which is proportional to velocity. The proportionality constant let us choose to be k. So the equation of motion is by Newton's law, second law of motion, this one, where this is mass into acceleration is equal to force, and the force is k into v. The negative sign takes care of the damping. It retards its motion, it opposes its motion. A bit of rearrangement leads us to this equation, and now we have to integrate. So this is the integration, and the limits are at t equal to 0. The velocity of the particle is u, which is the initial velocity, and at time t, suppose its velocity is v, which we are interested to find at present. And integration leads us to this expression. So this is the velocity, and we see that this term represents damping of the velocity. With the increase of time, the velocity reduces. When t was 0, velocity was u, which was the initial velocity, but as time increases, as we allow the particle to move on, the velocity reduces from u to v. So this is the velocity as a function of time. Now suppose particle has charge q and it enters normally a magnetic field B. So again B is down and the particle of charge q enters into the field. It experiences a B which exerts a force, Lorentz force on it, so it will just bend in a circle. So this is the circular track traced by the particle. Now on the circular track, the Lorentz force Q into V cross V supplies the centripetal force, which therefore leads to this equation, which on simplification gives us the radius of the circle. So radius is mv by qb. Now the velocity gets damped because according to the problem, the particle is also acted upon by a damping force, and therefore this v is actually of this type. Now if we put this value of v here, then we end up with this expression, which gives the radius of the particle as a function of time. We see that as time increases, the radius will decrease. So the particle will follow a spiral track as indicated here. So we have found the nature of path, which is spiral, the speed and the radius as a function of time. Let us extend this problem a bit and try to find the length that the particle traces. Now, since the particle traces a spiral track, it is obvious that it will soon fall upon itself. The radius is continuously decreasing, and after some time it will fall at the center. Let us try to find the distance traced before coming to rest. So this is mass into acceleration, and this is the force. and we can write it in this way. dv dt can be written as dv ds dt, where s is the arc length traced, and this ds dt is obviously v, and the v's on both sides cancel out, so we are left with this thing. And now we can simply integrate. Let us count distance from the entry point. So at the entry point s is 0, and at the entry point velocity is u, initial velocity, and after some time when the velocity is v, suppose the distance is s. So let us first find the relation between v and s. So that gives us this relation. Now ultimately after some time v is 0, and therefore from this equation if we put v equal to 0, we end up with s equal to um by k. So this is the distance traveled or spiraled by the charged particle in a magnetic field. This is another problem which speaks of a particle of charge q and mass m entering at the origin along I cap with an initial velocity of u into a region where there is a magnetic field along k cap. In this problem, b is not constant but varies with x. We have to find the maximum distance traveled along the direction of entry, that is along I cap. So this is I cap, and let us take k cap vertically upwards. So particle moves along I cap, it enters, feels a magnetic induction along k cap, which is in the vertically upward direction, and feels a Lorentz force in this direction, which is minus j cap. So this is the Lorentz force at the origin, which is along minus j cap as shown just now. The situation here is a bit different because the Lorentz force contains an x. So this means the particle will be deflected, or particle will bend along minus y cap, but it will not trace a circle, it will trace a curve. But here too the work done by Lorentz force will be 0, since f is perpendicular to the velocity, and so Lorentz force does no work, and therefore velocity is conserved, kinetic energy is conserved, that is the magnitude of velocity with which the particle entered into this magnetic field region will be retained. Now suppose this is the trajectory of the particle, this is I cap, this is j cap, the particle bends as shown, and this is the initial force that bent it. The particle at time t is here with velocity v. Now let us write down the force equation. So this is the force equation, Newton's second law of motion. Mass into acceleration is force, and the force is obviously the Lorentz force. We have written v explicitly. The motion occurs in the xy plane perpendicular to b, and therefore we can dissolve v as x component and y component, and therefore we end up with this equation. And we can now separate the I cap component and j cap component to end up with these two equations. The problem is to find the maximum distance along x. So let us have a look at the diagram again. The particle bends along this curve, and here it has a maximum x, which we denote by x0. We have to find this x, and we can do it from either of these two equations. Let us do it from the second equation. We replace dvy dt by dvy dx dt, and dx dt is vx, and therefore vx cancels out from both sides, and we end up with this equation, which can be integrated as shown here. Now we note that at the entry point x equal to 0, vx is u and vy is 0 because the particle had no component along jx. But when the particle is here, it cannot move further along x-axis, and this means its x component of velocity is 0, and it has only y component, and the value of y component will be equal to the total velocity because velocity is conserved. The total velocity is always u, and therefore when Vy equal to 0, then Vx is u, and when Vx is 0, Vy will be u. So we can put the limits that at x equal to 0, Vy is 0, and at x equal to x0, that is at x equal to x0, Vy equal to u. Integration gives us this equation. Now here we have a negative sign. Now let us trace its origin. We have to go back, and this negative sign is actually this one, and this one again comes from the cross product. In the initial equation also we had a negative sign which represented the direction of bending or deflection or curling. So actually this negative sign represents the sense of traverse of the curve, and therefore when we are making a calculation that involves magnitude only, because the sense of traverse of the path, whether it will be clockwise or anti-clockwise, right-handed, left-handed, etc., that matter has been solved, we can drop this negative sign, and therefore we have this equation which gives us x0, which is the maximum distance travelled along I cap, this distance. Let us consider the case of charged particle entering into a magnetic field. M is the mass of the particle, Q is the charge carried by the particle. The magnetic induction, let us take it to be along z axis. Now we consider three cases. Actually we consider two cases, and the third case will be a combination of the first two cases. And let me mention that we had already discussed everything about the first two cases. So in this lecture what we will do is simply stitching up things. We will be combining these cases we have already done, and of course we have to be careful about notations and symbols, which you can always change to what you feel more convenient or appropriate. Come to the first case, where charged particle enters into the B field in parallel. So V is parallel to B, and the velocity is denoted by V parallel, which is along Z axis, along which the B field exists. Now as V is parallel to B, V cross B is 0, and so the Lorentz force, which is Q into V cross B, will also be 0, and force 0 means particle will travel along a straight path. So the motion is parallel to B. Let us now come to the second case, where charged particle enters to the B field normally, that is in perpendicular direction. So now we denote the velocity by V perpendicular. As B is along Z axis, V perpendicular will be in the xy plane, and the radial direction in the xy plane we know is rho cap. This you did in the mathematical physics class. So V perpendicular is along rho cap. We did this elaborately in lecture 1C and showed that a negative charge follows a right-handed circle, while a positive charge traces a left-handed circle. Let us explain it once more very briefly. First, consider the positive charge, that is mod E. It enters into the B field along rho cap. It feels the B field which is upwards along Z hat, and therefore it is pushed by the Lorentz force, due to which it bends along this circle. So this is the track it has to follow due to the Lorentz force along this direction. The opposite happens to the negatively charged particle, which feels Lorentz force in the opposite direction and therefore traces this circle. And it is clear that if B field is along z hat, which is vertically upwards in this case, then the negative charge traces a right-handed circle, while the positive charge traces a left-handed circle, and the circles are of radius rho. This is rho. Now comes the third case, the oblique entry at angle theta with B field. As V is inclined to B at angle theta, we can resolve V parallel to B and perpendicular to B. The parallel component is V parallel and the perpendicular component is V perpendicular. This is resolution of V along and perpendicular to B. The effect of parallel entry with V parallel is moving along a straight line parallel to B, and the effect of perpendicular entry with V perpendicular is moving in a circle. So the combined effect will be a circle that is dragged linearly, which gives a helix, and the helix will be either right-handed for negative charge or left-handed for positive charge. So the problem is basically solved regarding nature of trajectory. We just have to determine the dimension of the helix, the radius and the pitch. The radius of the circle that makes up the helix will be, as before, rho, and rho is velocity by omega. Now velocity will be the velocity in the xy plane, because V parallel has no role to make the particle move in a circle. So the velocity that will appear in rho, which represents a circle in the xy plane, will be V perpendicular. V parallel will have no role in determining the circle. So we have rho equal to V perpendicular by omega. Omega, nu and t will be as before. They are velocity independent. Omega and nu, the angular frequency and the linear frequency, are called cyclotron frequency because charged particles trace circular tracks with this frequency in device called cyclotron, and we will discuss it in a future lecture. Again, to gyrate means to move in a circle or helix, the frequency of which is called gyro frequency. When we express radius rho in terms of momentum, we have to put mv perpendicular as done here. Another dimension of the helix is pitch. Pitch represents the amount of movement along the direction of motion in one full rotation. Now one full rotation occurs in time period t. So this distance is just the velocity along B multiplied by the time to generate this circle. So it is V parallel into t. So clear that the helix is traced because Lorentz force acts perpendicular to B and provides the centripetal force and makes the charged particle move in a circle, and the component of velocity along B pulls it along B. The tracing of circles is decided by the charge of the particle. Let me try to demonstrate these motions. This is the negative charge. So to describe its motion, we have to use the right hand, and this is B, and this is the manner in which it moves. so it is a right-handed helix. On the other hand, this is a positive charge, and to describe its motion we have to use our left hand. So this is B, and the positive charge moves in this way, so it is a left-handed helix. We can show it together. So this is the movement of negative charge. It is a right-handed helix with respect to the B, and this one is the movement of positive charge with respect to B. It describes a left-handed helix. So these are the two movements. So we have already got the results. Let us now formally introduce the theory, because if you are asked to describe oblique entry of charged particles in a magnetic field, then you can do it in two ways. One is, first consider the effect of parallel entry, and then consider the effect of perpendicular entry, that is V perpendicular, and then stitch them together. We can do it in a bit different way also, and this is as follows. Consider non-relativistic motion of a charged particle in a magnetic field, where B field is along z-axis and the entry is along the radial direction, and the polar angle is theta. M is the mass of the particle and Q is the charge of the particle. It may be positive or negative. So we have this diagram here. Rho cap is the radial unit vector in the xy plane, and this is the radial vector in the 3D. Now the velocity with which the particle enters into the magnetic field can be dissolved into two parts. One is the parallel component and the other one is the perpendicular component, and we can write it in this way. We can also dissolve V in Cartesian components, so that we have this equation. Clearly V rho and V perpendicular are same, and so are Vz and V parallel. The velocity magnitude is this one in terms of Cartesian components, and this one if we dissolve it in cylindrical coordinates, that is a rho component and a z component. The velocity magnitude is constant, and this is because Lorentz force does no work, and so kinetic energy is conserved, and therefore velocity is conserved. Now V perpendicular is actually the component of V along rho cap, this angle being 90 minus theta, and therefore this is V sin theta, and the parallel component is obviously V cos theta, and accordingly we have V perpendicular as V sin theta, which is actually V rho, and V parallel as V cos theta, which is actually V z. We can now write down the equation of motion of the charged particle in a magnetic field using Newton's second law of motion, and for force we have Lorentz force law, and therefore we end up with three equations. One is x equation, one is y equation, and the other one is z equation. Here omega is qb by m. Let us study the z equation, which gives us Vz is constant, and let that constant be a, and let that constant be a. So this is the z motion, and a simple integration gives us z equal to V parallel into t. V parallel is V cos theta, so z is V cos theta into t. Now this indicates linear movement along z axis. The motion will spread along z axis, and there will be no acceleration along z axis. This is because V parallel is constant. Also there is no force along z axis, and therefore it is a straight line movement. Now why no force along z axis? This is shown here. Let us evaluate Lorentz force. Lorentz force is Q into V cross B. We have written V explicitly here, and then taking cross properly we end up with minus phi cap. So Lorentz force is along minus phi cap, which is in the xy plane. So this means there will be no force along z axis, and due to this force in the xy plane, the particle will move along this circle. We can as before say that the particle enters along rho cap, sees B which is along z cap upwards, and feels a Lorentz force along minus phi cap, and therefore it just bends like this. and we get this track. So under this Lorentz force, Q bends and it traces this circle in the xy plane. So now the details of the xy motion. This will be an identical repeat of lecture 1C. So we will just copy the results of lecture 1C. This is the xy motion. We have assumed trial solution, Vx and Vy, C and D are constants, omega 0 the frequency of rotation, phi is the epoch. And if we put it in the x equation and y equation, we then get or arrive at this solution. Now here we have to be careful that Vx square plus Vy square under root is V perpendicular, which is a constant equal to C, and omega 0 is omega equal to Eb by m. Here E represents the magnitude of the charge of the particle, and V is actually V perpendicular square plus V parallel square whole under root. But in xy motion it is V perpendicular that comes in. Now for negative charge D equal to C, and for positive charge D equal to minus C, and things, if we do it correctly, we end up with this trajectory, and these are the centers, and this is the radius as we discussed earlier, and here V perpendicular is obviously V sine theta, the component of velocity perpendicular to B, that is in the xy plane. So we end up with this conclusion that motion in xy plane is a circle. Let us now make certain conclusions about velocity. These are the conclusions about velocity. This is the velocity magnitude, which in this oblique entry case has Vz square coming in, and this is actually a square and this is actually c square. So as stated earlier, V is conserved, velocity magnitude is conserved. The components Vx and Vy are dependent on time, but Vz is constant. We also end up with one important conclusion, that momentum in xy plane is m into V perpendicular, so it is mv sine theta, which is again equal to q rho b, and the pitch is h equal to V parallel into time period, so this is the pitch. So ultimately what we have is helical movements, right-handed helix for negative charge and left-handed helix for positive charge. Before ending, let me state that in the next lecture, entitled 1E, we will do more problems and we will study some application of charged particle in a magnetic field. Let me conclude this lecture with the statement of Pierre Trudeau, who was Prime Minister of Canada and whose motto was reason before passion. I do not really know what a cyclotron is, but I am certainly very happy Canada has one. It is very true that everyone will not understand science, but everyone should have respect for it. This is essential for development and progress, and this perception is badly needed by the rulers for betterment of the nation. Thank you.